is based on this concept called random walk through the graph. The concept is very interesting actually, because it's mathematically very interesting. You want to know, let's say you're now thinking about the web. Each node on the web, each page on the web is a node, and links between pages are directed edges in this graph. Now what we were looking at before is an undirected graph. Now we are looking at a directed graph where if a page points to another page, then there is a outgoing link. If somebody is pointing to you, then you have an incoming link. On this directed graph, you would like to know how important a certain node is. Okay? This question of importance, because there could be a spam node which connects into 1,000 nodes. Just because you connect into 1,000 nodes, you may not be very important. Okay? Or you may have 100 friends, all of you together decide that you should point to each other's pages. So a click of 100 edges, 100 vertices are pointing to each other, but they are really not pointing to the others in the graph. So they are also not very important, but if you see locally, they seem very important because they have so many incoming links. So neither on the basis of just incoming links, nor on the basis of outgoing links, you can tell that something is important. There needs to be some concept of a global importance of this node. How do you model that? Because if I have to look at everybody that's connecting to me and everybody that's connecting to them and everybody that's connecting to them, it becomes an unviable algorithm, right? How many levels will I step back? And this is a huge graph we are talking about. So the beauty of the core of the algorithm, PageRank algorithm that Brin and Page came up with is this. They said that assume that this is a graph and assume that somebody is walking on it randomly. Start from any node. If there is an outgoing edge to some other node, you could take it with some probability. And if there is no outgoing node, if you reach a dead end, then with some probability you can jump to any arbitrary node in the graph. If you walk on the graph randomly using this algorithm for a long period of time, how many times you visit a node indicates the importance of that. If there is a node where you can get to from many paths in this graph, it's likely that it's important. But if it's only local, then you will cancel out the importance because there is this one, there's a large set of vertices from where you cannot approach this. So your overall frequency, if you walk long enough, the number of times you visit the node will become less if it's only a local importance. So they said that if you take a random walk through the graph has two parameters. One is from any given point with about 15% probability you can jump into an arbitrary node. Randomly you can jump off into an arbitrary node in the graph. With 85% probability, whatever are the outgoing edges that you have, you will take one of them. And all those edges will have equal probability of taking. So if I have, let's say, 5 edges going out of my node, then I could take them, I'm oversimplifying this, I could take them at 17% probability. 17 5s are 85. The other 15% I'll randomly jump somewhere in the node, in the graph. When I jump, I have equal probability of landing anywhere, which is what I mean by randomly jumping. If using this little algorithm, we make a bot walk for 1 million years on the graph and count every time it visits a node, we increment the count of that node by 1. The number of times the node is visited indicates its page rank. This is the mathematical algorithm that Sergey Brin and Larry Page came up with. And you actually can write a theorem about this. You actually don't need to walk for 1 million years. You can solve this much more easily, this mathematical issue. So that's the basis of, that's the reason why we are studying random walks over the web. the amount of time that will be spent on any given page. This is assuming that when we say amount of time, we are not talking about the length of the content of the page. We mean how many times we visit, and there's a constant time that you spend in every visit. So the PageRank, the formula, mathematical formula that they came up with is this. PageRank of a page X is given by, there is a parameter alpha. Typically this parameter is set at 0.15, 0.20, that kind of value, 15%. So that parameter 1 divided by the number of nodes on the graph plus 1 minus alpha, and you have to sum up this, which is, the TT, these nodes, TIs, are all the incoming links that you have. You sum over all the incoming links, the PageRank of that node divided by the total number of incoming links that you have. So the out degree of T is, we are looking at X, the incoming node is T1, T2, T3, T1, T2, Tn, I'm sorry, and given page X with these inbound links, then your PageRank is calculated based on the PageRanks of your incoming nodes.
Can you explain on C of T? What is that?
C of T is if Tn is connecting to me, but Tn is also connecting to many other people, then my importance is not as much. If CNN.com connects only to me, then I am probably some big shot. But if I am one of the million people that CNN.com is connecting to, even though CNN is important, I should not get a lot of that. So that's what is happening here. We are dividing by the out degree of the previous node. We are weighing it down. So Ct is the out degree of T, alpha is the probability of the random jump, and n is the total number of nodes in the graph. Total number of nodes in the graph really, if we are looking at this parameter n for all the nodes, and we have a PageRank for all the nodes, and we are only comparing the PageRank at the time of listing out Google results, then really that factor will not be important, because it will get cancelled out for all the pages, because the total number of nodes in the web doesn't change across the pages. So our goal is to implement this on MapReduce, this algorithm on MapReduce. So from that perspective, it's important to see that this is very similar to what we had done earlier. Earlier, we were given a node and all the nodes that it is connected, adjacency information we were given. Now, for calculating this function, we need the node and all the incoming links, not the outgoing nodes. Other than that, if we know the incoming links, this formula is just an iterative way of incrementing my PageRank, of refining my PageRank. If I know the PageRanks of all the people that are all the nodes that are connecting into me, my PageRank can be recalculated. If I know the PageRanks of these guys and the out degrees of these guys, then my PageRank can be calculated. Are you with me there? And once my PageRank is calculated, could it change?
Yes.
It could, because the changes happen because of the cycles in the graph. We don't know how many cycles are there in the graph. So when you iterate, there may be a second path to get to me. Hence, you will come to a predecessor of this node X again. So X PageRank will need to be refined. And you need to keep refining it like this until you come to some steady state, which is what we had in the Dijkstra algorithm also. Oh, tell me, can you conjecture how many times can the MapReduce cycle run in the Dijkstra's case? Dijkstra algorithm. We said MapReduce needs to be repeated, iterated. Maximum how many iterations can be there? N-1. Where n is? Number of nodes. So if you have 100 nodes, you cannot iterate 500 times. So would that apply here also? Can you keep going infinitely here?
There is a possibility. There is a possibility.
Is there a possibility? So there is a possibility. There are, this is one of the shortcomings of the theoretical PageRank algorithm. Practically there could be many fixes for it. But it could, two nodes can keep increasing each other's PageRank. You could get into a situation. But assume for now that we have a way of handling that. And that's a very rare case, and assume that doesn't happen. Here also we can have a very similar MapReduce program design and iterate over it till the PageRanks become stable. What we mean by stable is you define some say threshold for the amount of change that should be there cumulatively in the PageRanks from iteration to iteration. So if PageRanks do not change much overall from between two iterations, then you stop. So computing the PageRank, the sketch of the algorithm is like this. You start with seed PageRank values, which is some arbitrary but assigned without bias. Some values which are assigned without bias, and each page distributes some credit to all pages it links to. And each target page adds up credit from multiple inbound links to compute its own PageRank. So it's actually a two-way operation, and then you iterate until these values converge. We will not show the actual MapReduce code for PageRank, but if you understand the previous Dijkstra code very well, you can write this by yourself. And I encourage you to write it by yourself. Okay. So the map step for PageRank, you distribute the PageRank credit to all the targets, all the links out of a certain page. This, the PageRank of this gets distributed between all the targets that it is connected to, likewise for everyone. And the reduce step actually gathers the PageRank credit from the pages and accumulates them to compute the new PageRank. So in the map step, you take your PageRank, you know who all you are connected to because your adjacency list is given. So distribute your PageRank to those guys based on how many people you are connected to. So if my PageRank is, let's say 100, and I am connected to 10 nodes totally, my contribution to each one will be 100 by 10. So add 10 to each of their PageRanks because my PageRank is high. And in the reduce step, accumulate those 10 to compute the PageRank, or you have gotten the contributions from multiple people that are connecting into you. Let's say I connect to these three nodes. So mapper will take my PageRank value, load it in some way, weight it in some way, and add it to these guys. So this guy's PageRank gets incremented based on what my PageRank is. Similarly, this guy may also be connected to by another node. So the mapper that is running this job will give another increment based on this guy's PageRank. And the reducer will get all of these values and accumulate it. Yeah? That's what we are doing here. Reducer gathers up PageRank credit from multiple sources to compute the new PageRank. And that iterates until convergence.